Okay, we are continuing with our sessions on this course of organization and analysis of large data sets in health care, which in the curriculum is known as the health data set organization and analysis. In this session, we are going to talk about formulation of a data analytic plan and go through the various parts or the various formats that can be used. And we're also going to tackle issues regarding data analysis, which I would call the preliminary issues that everybody needs to know. And we shall go through the process, theoretically what the processes are, and then we shall delve into the practical sessions, which will be probably 2 to 3 sessions, at most 4, but 3 should be enough. So we alluded to the issue of a data analysis plan, and we said in the last session that a data analysis plan is a stepwise, logical, and coherent plan on converting data from its raw state to the final results. So it is a pathway of obtaining final results from raw data. That pathway should be stepwise, logical, and coherent. So now we are going to look at a theoretical example on how to draw a data analysis plan. Please remember that in our previous session, we said that drafting a data analysis plan starts with literature review. As you are doing your literature review, you are obtaining this information, and you are summarizing the information you've obtained. You're also looking at how other people actually analyze the data or presented results on the same topic that you are going to work on. And some of the things that you look at during the literature review that are pertinent and important for data analysis include the outcome variable, indicator variable. It's important to know that the results of our studies usually get compared and contrasted with previous studies in the same area, unless, of course, the topic is completely new, or the paper is absolutely novel in its way. But you know, there are not very many novel papers in health sciences, but of course they are there. They appear in journals usually like in Nature and Science. Most of us are probably not to that level yet where we can publish papers in those journals. So when you are doing analysis, please make sure that you pay attention to the following. Sorry, let me retract that. When you are doing literature review, please make sure that you pay attention to the following issues that are relevant and highly related to your analysis plan and actual analysis. The first is the outcome variable or indicator variable. And remember that the correct choice of an indicator variable helps to have smooth data analysis and a good write-up on presentation of your results. When you look at the outcome variable, remember the difference we talked about between an endpoint and an outcome variable. We discussed this in the last session. In many cases, especially in cross-sectional studies, the endpoint is also the outcome variable. But we saw that in follow-up studies, cohort studies, and time to event studies, the endpoint is not necessarily the outcome variable, but rather it helps to create the boundary for the outcome variable. So you look at the outcome variable and assess what is the outcome variable. As you do literature review, what is the nature of the outcome variable? How do people in previous studies, how did they analyze it? Did they analyze it as a count, Do they analyze it as just a number? Do they analyze it as a proportion? Do they analyze it as odds? Do they analyze it as a rate or as a risk? And these are all have different implications. Also, you check to see if they analyze it as a time to invent, and so you note that. And the reason you note that are multiple. One, you have to determine whether you are going to use the same outcome variable and in the same nature and format of the outcome variable. And two, recall that the nature of the outcome variable determines the method of regression analysis. In fact, not regression analysis only, but even the one of measures of central tendency and measures of dispersion. And three, you look at the outcome variable and its nature to see if you can come up with the same in your secondary data. So, for example, the outcome variable may actually be, the outcome variable may exist in the data set, your secondary data set, as one variable. Assuming you're looking at, for example, let me say birth in the last 12 months. It's birth. Did the woman give birth? If you are using, if you are looking at HIV incidence, did somebody become HIV positive? It could be just one variable. But there are also outcome variables or indicators that require multiple variables in the data set. For example, it could be your outcome variable could be BMI, body mass index. And we know that body mass index is calculated from body weight in kilograms and height in meters squared. So in that case, once you know your outcome, your indicator variable, then you look into the data set to see if you have a covariate or covariates that will help you to get the outcome variable. That is a very important step in data analysis, because if your secondary data does not contain variables that will help you to come up with your indicator variable that you are going to analyze, then you cannot use that secondary data. So that is something important that comes right from literature review, and it has indications on data analysis. The other part that has indication on data analysis that springs from literature review, you also look at the method of analysis that was used. And I want to put these things on the board now. So the first thing we look at is the outcome stroke indicator variable. As you are doing literature review, you've got to look at that, and I've explained why. Then, of course, you look at the method of analysis. So, how did the people in previous studies analyze? How do they conduct the analysis on the indicator variable? And again, the importance of that is to find out, first of all, was it the right method of analysis given that indicator variable? And two, do you have what it takes in your data set to conduct the same analysis? And basically, the nature of the data collection and the nature of the data set will determine and limit one's ability to conduct some forms of analysis. If the data are purely cross-sectional and there is no follow-up element implied in the data or actually existing in the data, then it is impossible to analyze this data as a before and after, or to analyze this data in form of occurrence of the outcome at a later time given the start of the exposure. So that is also something to look out to when you are doing literature review, that also has implications on data analysis. The other part that to look out to is which confounders which confounders did people in previous studies adjust for? Third thing is confounding variables or confounders. As you review literature, you will actually see that in this study X, the outcome was this, the method of analysis was this, and they adjusted for these confounders. And they give the reasons why they adjusted for them. And so the issue it would raise for you would be, do I have the same confounding variables in the secondary data set that I'm going to use? And more than that, you got to know which of those confounders was or is a major confounder, meaning that you go to adjust for it if you're going to present any good data on that subject. And then if those variables are not in your data set, then you get into a problem that we teach in epidemiology known as residual confounding, meaning that you would have loved to have 10 confounders, including variable x, y, and z, which are major confounders, but you only have x, you are missing y and z, and out of the 10, you only have 5. So automatically, it goes without saying that even though you are going to adjust for those 5 variables, you would not have completed all the adjustment, meaning that you will remain with residual confounding. So this is something that is also important to look out for. The other thing during literature review that you look out for, that is again related to data analysis, is how people handled the categorical data and how did they construct their categories. In other words, most of the variables that are turned categorical include age. Age is the commonest variable that is categorized. And we do encourage people to correct continuous variables in their raw form and not in categories. But if they want to categorize them, then they can categorize them at analysis. And so the fourth thing you look out for is categories of variables. The categories of certain variables that are categorized. Okay, and I'm going to spend some good time in this session to talk about categorization of continuous variables. So we are now going to switch our attention specifically to categorization of continuous variables. So we now move to categorization of variables. So categorization of variables, categorization of continuous variables. Okay, so categorization of continuous variables. There are reasons why people choose to categorize continuous variables. But I need to mention from the outset that a continuous variable can actually be analyzed as continuous and interpreted even in regression as a continuous variable. Many times people categorize these variables, particularly when they are independent variables and not the outcome variable, because they want to simplify their interpretation, or they expect the association to differ within certain categories or ranges of a continuous variable, so they do not necessarily want to leave it as a unity change in a continuous variable. And usually what drives this is the relationship between that continuous variable and the outcome. The relationship may be random which is known as, some books write as stochastic. Maybe stochastic or random, meaning that if you plot a correlation between that outcome, the outcome variable and the continuous variable, the changes in the continuous variable start, in the independent variable start right at the time of the change of the continuous variable. Sometimes it is non-random or non-stochastic, meaning that the continuous variable has to accumulate a certain level of exposure before it can start to show its changes with the outcome variable. And so, in that case, it becomes easier to actually categorize the continuous variable because its association with the outcome variable depends on certain ranges of a continuous variable. But now, when you do literature review, you have to you find out how did previous studies categorize their variables, and you may choose to follow the same categorization, or you may choose to use your own categorization, as long as you justify your choice. And one of the reasons why people choose to follow the same categorization is because they want their findings to be compared and contrasted with with those of the previous studies. And so they don't want to be comparing different categories since they want to do that comparison. But also, some people keep the same categories because of ease, because somebody else has already figured out that there is a uniformity within those categories and there is differences across those categories. You may actually choose to make your own categories. You don't necessarily have to agree to the previous categorization as long as you can justify and defend your categorization. There are some reasons that underlie categorization of continuous variables, and so we should not just categorize variables for fun or based on gut feeling. There should be some rationale, justifiable rationale for categorizing the variables. So, and I'm going to go through some that I have taught over the years. So one is homogeneity or uniformity within the categories and heterogeneity or differences across the categories with regard to the association between the independent variable and the dependent variable. So one of the reasons should be homogeneity within the stratum or categories, within the stratum or strata or categories with regard to association between the independent variable and the dependent variable. In other words, when I decide to make a category, for example, let's go for age, and I'm looking at an outcome like a hormonal contraception use for females. When I choose to categorize 13 to 17 years, I should be able to justify that the girls from 13 to 17 years are similar in their behavior with regard to use of modern contraception. Therefore, I can lump them together rather than having each age group alone. But otherwise, if the 14-year-olds completely differ from the 13-year-olds with regard to how to use modern contraception as a dependent variable, then it is not logical to combine 13 years and 14 years in one category because they differ with regard to the association. So this issue here, homogeneity, that means that there is similarity or uniformity. So when we categorize that age group and say 13 to 17, we must combine them into one category, knowing that their association, the association between people in that age group and the outcome is actually similar. So that 13, 14, 15, 16, 17 tend to behave the same way with regard to the outcome. Therefore, they can be combined. Now, the second reason is now the converse or the opposite of the first, heterogeneity. And everything, heterogeneity across the categories. And everything else is the same up to here. So heterogeneity meaning difference. So that so if I do 13 to 17 and 18 to 24, I automatically imply that the 13 to 17, they are similar, they are homogeneous with regard to their association with the outcome. So that means I can lump them together. But the fact that I've created another category of 18 to 24 means that this category differs from this category with regard to the association with the dependent variable. If this category from 13 to 24 is the same, if these are the same as these, then I have no reason to do 13 to 17 and cut off and then do another 18 to 24. If they are not heterogeneous, in other words, if this group is not different from this group, then it makes sense to make one group which is 13 to 24 because they are uniform. So the reason we create other categories is because these categories within themselves they are uniform, but across the categories they are different. That is the heterogeneity. Now the other reason that people do categorize variables is because of numbers, distribution of numbers or observations in various categories. So now, for example, you may have enough numbers in some categories, but have very, very few numbers in other categories. You may find that when you going back to our example of hormonal contraception used in females, you may find that you have adequate numbers for the lower ages up to like 45. Now, when you go to 50 plus, you discover that you have a category of 50 plus, but there are only 3 people in that category. Because and that could be reasonable because most of the women may have already reached menopause, therefore they don't see any risk of becoming pregnant, and so they are not even using contraception. But then you get into an issue of parametric methods of analysis. As you recall from Applied Biostatistics 1, that chi-square requires at least each cell to have an expected number of 5 in each cell. Now, if the numbers are so few in some categories and you are going to use those parametric methods of analysis, then you are going to violate those assumptions. So somebody may end up saying, I know I would have had this category as the extreme, but there are very few numbers, therefore I'm going to combine them to the next category to have adequate numbers, or I'm even just going to totally eliminate that category. So that is also another reason. But this reason is not as strong as the first two reasons. And then the fourth is what we've already talked about, previous studies. And so people may categorize a continuous variable in a similar manner to the previous studies because of the compare and contrast. Because of the compare and contrast. They want their findings to be comparable to those of previous studies, and this comes out in the discussion section of one of the results. So the take-home point here is that a categorization of a continuous variable is not just a random thing. It's not just based on gut feelings, but it has some, it is rational, it is logical and rational based. And one should be able to justify the categories. Over the years, I've had many students ask me, should the categories be equal number? In other words, the distance between the categories, should it be uniform? It doesn't necessarily have to be uniform. I think uniformity is not as strong a reason as homogeneity, and homogeneity within the category and heterogeneity across the categories. You may find that some categories may have a narrower width, while other categories may have a larger width. For example, you may for HIV, you may categorize adolescents alone, and then anybody from 18 to 24, for example, you may also give them a different category because of the behavior issues that are pertinent to them. But then from 25, you don't necessarily need to set 25 to 29 and create 5-year categories. You may actually move from 25 to 35 or 34 because of the uniformity of that group with regard to their exposure behaviors and also with regard to the outcome. So long answer made short, the categories need not be same width. But of course, if they can be same width, it is also, it makes it easier to interpret. Now, the things we've got to be careful about making categorical categories out of a continuous variable is making sure the categories are mutually exclusive. It's a very important thing. When you make categories of a continuous variable, please ensure that the categories are mutually exclusive. Categories should be mutually exclusive. Mutually exclusive, meaning that if you have, each category should have a lower and an upper boundary. Lower and upper boundary. So the upper boundary of one category should not be also the lower boundary of the next category. They should be totally and mutually exclusive. For example, you cannot have 13 to 17 and then have 17 to 24. Because now the question is going to be, where do we put the 17-year-old people? Do we put them in this category or do we put them in this category. Because in this category, they are in the upper boundary. In this category, they are in the lower what? Boundary. So that means that this category and this category are not mutually exclusive. And so to make them mutually exclusive, this category should be 13, should not be equal to the upper boundary of another category, so that they are mutually exclusive. Otherwise, that can be a problem. And please note that while this is something that you should always pay attention to, we should also be careful when you are dealing with software to create those categories. We should also be careful not to actually make them mutually exclusive. Because on paper, in our tables, they may be mutually exclusive, but in the real data set, when you created these categories, did you make them mutually exclusive? That is quite important. Now, the other thing that we have to pay attention to when we are dealing with the category, when we are categorizing a continuous variable, is the issue of, so the other thing we have to be sensitive about is the issue of missing data. Missing data. So depending on which software you are using, you've got to understand the default of missing data. So in Stata, for example, Stata takes missing values. For example, Stata, in Stata, missing values are taken to be huge. Their missing values are like a positive infinity. They are huge. So when you are constructing a variable, a categorical variable, and there are some missings, and you don't attend to that, the missings will be included in the last category where your variables were high. And let me run through we shall say practical, but let me just demonstrate. If we have age, and it ranges, the range is from 13 to 56. And then we have 5 people, 5 observations that are missing age. When we start generating categories, and we start to generate a category of 13 to 17, then we say, okay, create one of 18 to 24, create one of 25 to 34, one of 35 to 44, and one of 45 plus. Now, when we ask Stata that please generate this variable, and maybe we can call this category 1, category 2, category 3, category 4, category 5. If we tell Stata that generate category 5, if age is greater, and we just say age is greater, if age is greater than 45, then Stata will include everybody who is 45 and above, including the 5 that are missing. Because for it, anything that is missing is taken as a greater value. Whereas now, if we know that it is missing, we'll tell Stata that generate this category, that is what? The category 5, if age is greater than 45 and age is not equal to missing. So it would take people whose age is 45 and above, but not missing, and replace them into this category. That way, we would have avoided the missing. And again, depending on your proficiency with Stata, instead of using the generate, replace commands, you can use the record. And the record command will help to eliminate this problem of including the missing values as upper values. So those are things that one has to pay attention to. Again, when you categorize, again, the other thing, once you categorize the variable, a continuous variable, it is important to label your variables according to your categories. And so let me theoretically run through a command. And again, let me use the example of age. So we have age, and this is a variable. It ranges from, range is 13 to 56. And then we have observations that are missing equal to 10. So 10 people are missing age. So we want to create categories. And I'm going to use green for starter commands. So we can actually use two approaches. We can use the generate, replace. So that is one. And so our task is to create age categories. Age categories. So there are two ways. One, we can use the generate and replace commands. Or two, we can use the record with comma generate command. Either way, it gets us to what we want to achieve. So let's start with the generate and replace command. So we can come up and say, tell stator, generate a new variable known as age underscore category, age cat, is equal to 0 if our original age is greater or equal to 13 and age is less than 18. Now, which category have we created here? The category we've created here is that of people ranging between 13 to 17. Why? Because we've told the stator generate a new variable known age cat. Its value is equal to 0 if the original age variable is greater or equal to 13, meaning it starts with 13, and it's also less than 18, means it stops at 17. Then, under the replace, we go ahead and say replace, because we cannot generate this variable again. We've already generated it. So say replace age cat is equal to 1 if, and the reason we say replace is because anybody, when you say generate, age cat is equal to 0. If age is equal to greater or equal to 13 and less than 18, everybody who satisfies this criteria, stator is going to give them 0 for age cat, but everybody else is going to be missing. So now we say replace. We are now replacing the missing. Replace age cat is equal to 1 if age is greater or equal to 18 and age is less than 30, for example. And here we've created a category that is 18 to 29. Okay? And that goes to 29.99. Then we create another category. Again, we say replace age cat is equal to 2 if age is greater or equal to 30 and age is less than 40. In that case, we are creating an age bracket that is 30 to 39. So, and then we can now say maybe we want the last one to be 40 plus, and say replace age cut is equal to 3 if age is greater or equal to 40. And now this is where the catch comes in. If you leave it like that, age greater or equal to 40, even these people who are missing age will be included in this category. So the thing is, you have to state if age is greater or equal to 40 and age is not equal to missing. So that means only those people who have values for age should be included in this category if they are greater or equal to 40. Anybody who has missing for age should not be put into this category, because you don't know whether the person who is missing age would have been 15 and therefore be in this category, or would have been 20 and in this category. So once you don't put this last part of age not equal to missing, Stata will give everybody who is 40 or more, including the missings, we put them in category 3. So that's why it is important to use this command. And now, once you've done that, you got to remember that this is your category of 40 plus. So now, instead of leaving this variable in the data set to appear as 0, 1, 2, 3, it is wise and advisable to record these categories so that when the figures come out or when you do analysis, instead of coming out as 1, 2, 3, and you start struggling, what was 1, what was 2, what was 3, they come out as the actual age brackets. So you now go and do a label define. So you define a variable, label define. Label define, and let me call this variable new age. New age. This is just a dummy variable, not a real one. It is a variable that is going to carry the labels we have here. New age, and I say 0 is 13 to 17, 1 is 18 to 29, 2 is 30 to 39, and 3 is 40 plus. Then, once I've generated this variable new age, which has these, it's a label variable, which in which 0 is labeled this, 1 is 2 and 3 are labeled that. Then I tell Stata, please label the values, age cut according to new age. So it will get where there is 0 in age cut, it will put 13 to 17. Where there is 1 in age cut, it will put 18 to 29. So that when you analyze your data, for example, you say tab age cut. In this table, things will come out as 13 to 19, it will give you the number and the percentage. Then 18 to 29, 30 to 39, 40 plus. They will come out as the actual labels instead of coming out as 0, 1, 2, 3, and then you start struggling what was 1, what was 2, what was 3. So this is the importance of making sure that you label those variables. Of course, there are many ways of doing this in Stata. I'm just giving you the simplistic common way, and as those of you who are well versed with the programming, you can actually reach the same results using a different way, as long as you are comfortable and confident about your programming. So we can also use the record command, okay? And say record, then we are recording the variable called age. And then we say anyone who is 13 through 17 is equal to 0. Anyone who is 18 through 29 is equal to 1. Anyone who is 30 through 39 is equal to 2. And anyone who is 40 to 56 is equal to 3. Then you put a comma and you say, after you've recorded this age, then generate a new variable, which is age cut. So that way, you are avoiding the issue of missingness because you are using 40 to 56, which is the actual range. You know the range, the upper range stops at 56. So here, you are not going to include these missing people. Of course, after that, you again have to do the label define and label values. So this is the this was a demonstration on how to be careful, deal with the missing as you categorize continuous variables. Very important. Now, the other issue that we want to talk about briefly is the effect of missing data. It is beyond the scope of this course to go through the methods of imputation and how to impute data. But at least one thing you've got to remember, that missing data affects your sample size. Okay? Missing data affects your sample size. When you finally analyze this data, you may find that people who are missing in certain variable, they are actually not missing one variable, but they are missing another variable. And so, for example, if we have these observations, let me do a simple illustration. We have ID 1, 2, 3, 4, 5, let me do 7, 6, 7. Now we have variables, and here is age. This person has age, this one has age, this one is missing, this one has age, everybody else has age except ID 3. Then we come to sex or gender. This one is missing, it wasn't corrected or it wasn't recorded, everybody else has it. Then we come to education. You know, education, and everyone has education. Everyone of the 7. Okay? Then we come to residency, residence or resident status, and everybody has it except number 7. Okay? Now, when we have such a scenario, you realize that each of these 7 people, whichever variable is missing, only one person is missing. And for age, it is this one, number 3. For education, it is for sex is number 1. For education, no one is missing. For residence, number 7 is missing. For income, number 6 is missing income. Other people have income data, and number 6 is the one missing income. Now, what happens is that when you go to run your regression analysis, for example, when you are using Stata uses what we call complete case analysis. So if you put in your model and you say it might be a regress model, it may be a logistic, and you say regress, you put in your Y and you put in age, sex. And assuming nobody is missing the outcome variable. The fact that this person is missing age and this one is missing sex, the only observations that will contribute to this analysis are 5. 5 observations. Why? Because this one missing age will be dropped and this one missing sex will be dropped. And then for you, you may not actually know that your sample size is shrinking as you add more variables. So then you may add all the variables and say regress I, Y, then you have age, sex, education, residence, and income. Now, since you've added all, the computer will use only those who have complete data on each of these variables. And guess how many you'll be dealing with? It will be who has data on all those variables. This one, so this one is one of them. Who else? This one. Those are 2. Who else? This one. Those are 3. So the observations, once you add in, the observations that will be used in this regression are only 3, because they are the ones that have complete data on each of the variables. So you can see how quickly your sample size can shrink because of missingness. And this is something that one has got to pay attention to. Of course, there are ways in which you can change the default from complete case analysis to what we call available case analysis. Available case analysis. But this requires working with a biostatistician to help you do this. So I hope this really illustrates the importance of missingness, its effect on what we call the effective analytic sample size, and also its effect on categorizing continuous variables. So those are issues that one has to pay attention to. And so we will take a break and then continue with a follow-up session after here. Thank you.